Hey guys, this is Carl, and this is week 6 and problem number 3, and so we'll go ahead and just kind of dive right into it. So, a sample of 77 games sold for a new gaming platform has prices that have distribution that is skewed to the high end with a mean of $5.14 and a standard deviation of $2.87. Teens who own this platform typically own about 32 games. You can kind of tell, just kind of policy-wise, $5 is the mean. It's not too bad, not too bad deviation. Using the 68, 95, 99, 7 rule, draw label an appropriate sampling model for the average amount a teen would spend per game if they had 32 games, assuming those games were a representative sample of available games. And remember, kind of talking about representative sample, it's a sample that's it's indicative of the population, characteristically, either by race, ethnicity, age, those kinds of things, location, geographic. So representative means kind of, okay, does this sample represent, in essence, the population that you want to look at, either it be a city, a state, those kinds of things. So even though distribution that is being sampled is skewed, sampling distribution should be normal. Assume that the sample size is large enough and the observations are independent. The normal model for the sampling distribution of the mean has a standard deviation given in the equation below, where omega is the standard deviation of the population and n is the sample size. When omega is unknown, use the standard deviation of the one real sample as the estimate. So the standard deviation of the sample is $2.87, and the sample size is 32. So just a quick Excel calculation, 0.5 is our value. So, and you can see up here, just as we were explaining it, 2.87, standard deviation, which is O, and the square root of 32. 32 is our inset size, so 0.57. So, just kind of recalling this distribution of a 68, 95, 97 rule. Rule can be used to determine the percentage of data that lie within the k standard deviations of the mean, k being the number. Be 1, 2, or 3 standard deviations. Now remember, and it kind of we explain it here. 6895 states that unimodal. Unimodal, what's that mean? Good rule of thumb, just like what we've explained before. It's one peak. Unimodal, there's one curve, or one bell curve rather. Bimodal or multimodal could be multiple peaks within a given time frame. And symmetric, just as it sounds, it means that it's equal distribution. That split the graph right down the middle. It'll be equally, both sides will be equal. And so 68% of the values fall within 1 standard deviation of the mean, 95% within 2, and virtually all, 99.7, fall within 3. It's a rule in distribution, and you can kind of see it here graphically is what we're talking about here, just to kind of explain to you how this is calculated. We scroll down just a little bit, and you can see. Now remember our equation, 0.57. See our values, -3, -2, -1. This value, 5.14, it's calculated using this. And as you can see, what it is it's these values that we have, starting from here. See, 5.4. Remember going back up? Our 5.4 is our mean, up here, 5.4. So split right down the middle. Our mean and distribution is here. We want to see just the distribution of other games within 1, 2, or 3 standard deviations. Now remember, this graph, negative and positive, it's still 3 standard deviations, but it's almost like a confidence interval in the sense of you want to get 3 up and 3 down. You want to get both spectrums, and as you can tell, being less than that. So really what you're calculating is really -3 times 0.5, -2 times 0.5, -1 times 0.5, and then with the 5.4. Now what that means, key point is to remember just exactly how you get these values. So think about it this way, -1 times 0.5. So in essence, you're getting kind of almost 0.5 back. So 0.5, or -0.5 rather. So -0.5, adding that to this value. So -0.5 plus the 5.4 will get you around the 4.6, and vice versa. You multiply this, -2 times 0.5, adding it to that will get you these values. So you kind of see what these are, and then you can kind of see the percentages wise in terms of just the distribution itself. So this is a good kind of introductory way to kind of get you thinking about when you say of the 68, 95, 99.7 rule, and then exactly what that looks like literally. What does that look like? And then the cost wise, if this is the mean, what's the value when it's 68% out, that kind of thing. So we just hope this helps, and just let us know if you have any questions along the way. Thanks so much.